In this video, we're going to look at geometric sequences and series. To begin with, let's define the terms sequence and series. A sequence is a set of ordered terms generated by a rule. An example might be a sub n is equal to 2n plus 1, where n is greater or equal than 1. So we could generate the first 4 or 5 terms by simply subbing in values of n. So let's go ahead and do that. Let's have n equal to 1, 2, 3, 4 and 5. The term in the sequence a sub n, if I put in 1, a sub 1 is 2 lots of 1 plus 1, that's going to give me 3. If I take n to be 2, a sub 2 is 2 lots of 2 plus 1, that's 5. If I take 3, a sub 3 is going to be 2 lots of 3 plus 1, which is 7. We'd have 9 and 11. So the first 5 terms in this sequence are 3, 5, 7, 9 and 11. We can see that this is an arithmetic sequence with a common difference of 2. A series is the summation of the terms in a sequence. We might show the series now using sigma. Sigma is the Greek to sum. So the series, and we'll take n from 1 to 5 of a sub n will be equal to 3 plus 5 plus 7 plus 9 plus 11. So we can say the sum of the first 5 terms of this arithmetic sequence will give us now 35. So when we're looking at a sequence, we can see that we have the commas. When we're looking at a series, generally we'll have plus in between them. So sequence is the collection of terms. The series is the summation of the sequence. With this particular sequence, we have the common difference. So we say that this is arithmetic. A geometric sequence has a common ratio. So each term in the sequence is multiplied by a constant value, and we call that r. And that generates the next term in the sequence. A nice informal example would now be a bar of chocolate. So let's go ahead now and just sketch this up. Say I started off with a 1,000 gram bar of chocolate, or a kilogram bar. If I eat half of what's left each day, I end up getting a smaller and smaller amount. So on the first day, I'm going to have now 1,000 grams, or a kilogram. And what I'm going to do is eat half of this. So if I eat half of it, I've got now 500 grams left. So the next day when I go to the fridge and take this out, I've got 500 grams left. If I eat half of what's left, I'm going to end up the next day with 250 grams. So I've got 250 left. So we can see that this is halving each time. Then the next day, I'm going to have now 125. And then following that, I'm going to end up with 62.5. So 125, and then we can cut this up. And the next day, we'll have 62.5. I'm simply eating what's left now, half of what I've got left. If we look at this now as a geometric sequence, the first term is 1,000. The second term is 500. The third term is 250. The fourth term is 125. The fifth term is 62.5. And this will go on and on. If we look now, we've got a common ratio of 1/2. We can find that ratio by dividing backwards. So if I did 500 divided by 1,000, I get half. 250 divided by 500 is a half. 125 divided by 250 is a half. 62.5 divided by 125. As you can see, we're going to get smaller and smaller. This is going to tend to 0. Now, if this particular sequence is going to tend to 0, we can say that it's going to converge. Later on in the video, we will look at what it's meant, or what is meant by a convergent and a divergent sequence. In general, we can say that the nth term of a geometric sequence a sub n is given as a multiplied by r to the power of n minus 1, where a is the first term, r is the ratio, and n is the number of the term in the sequence. So if we look at my chocolate bar example, this is going to be now the first term in the sequence. This would be the second, this would be the third, this would be the fourth, and this would be the fifth, and so on and so forth. So what we can see is we've got 1,000. That's the value of A. The ratio we've already established now is going to be 1/2. We've got now n minus 1. So if I take 1, 1 minus 1 is 0. So 1/2 to the power of 0 is just 1. So I could say now that a sub 1 is going to be equal to 1000 multiplied by the ratio, which is going to be 1/2 to the power of 0. And we can see that that's just going to give us 1000. The second term, a sub 2, is going to be 1000 multiplied by 1/2. Now 2 is going in, 2 minus 1 is 1. And we can see from here, and let's just put this here, we can say that a sub 1, the first term, is going to be 1000. We've got the second term, a sub 2, is going to be 1000 multiplied by 1/2, which is 500. We can see now the next one, a sub 3, is going to be 1000. Remember, a is our first term multiplied by 1/2 to the power of 2. So that's going to give me a sub 2, and it's simply going to give me 1000 times by a quarter, and we can see that we're generating terms now in this particular sequence. So if I wanted now the 20th term in the sequence, I would simply now sub in here 20. So I'd have a sub 20 would be 1000 multiplied by 1/2 to the power of 19, as it's n minus 1. So if we look now at the 20th day in this particular sequence, we can see now that we're going to have 1000 multiplied by 0.5 to the power now of 19. So this tells me how much chocolate I'm looking at getting, and that's pretty small. So as we can see, as n gets very big, this now is going to end up being a very small number. So if I took now my general definition, and this is something that you'll need to learn, this is the nth term of a geometric sequence. If I wanted to write the nth term for my bar of chocolate, I could say that a sub n is going to be 1000 multiplied by 1/2 to the power of n minus 1, where n is going to be greater or equal than 1. So this now is given a formal definition for now my bar of chocolate. So we could pick any term in that sequence that we wanted. With sequences, we've got 3 different results. The sequence will either converge, and as we can see that this is going to tend to 0, or it will diverge, or it will oscillate. If our ratio is taken to be now, the modulus of the ratio is less than 1, then this will converge. So we see now that the ratio of positive 1/2 means that this is going to get smaller and smaller, such that it will tend to 0. So we say now that if the modulus of r is less than 1, the sequence will converge. So let's put this just here. So if we say that, that will converge. If the modulus of r is going to be greater and strictly greater than 1, then it will be a divergent sequence. So we will have now that it will diverge. So let's look at an example of a sequence that might diverge. Let's say I put now £20 into the bank and they gave me 5% interest. So I multiplied it by 1.05. Now, we would have here to the power of n. Let's just take this now. Let's say the value of this after n years, let's just put the value, will be something like so. So after 1 year, it's going to be 20 multiplied now by 1.05. Now, after 10 years, that value is going to get greater. So in the 10th year, we could say that this value was going to be 20 times 1.05 to the power of 10. If I was still around in 1,000 years, that term is going to be massive. So the sequence in the term is now going to get huge, and there is no limits, or no limit I should say. So as n gets very big, this term in the sequence will also get very big, such that it diverges and it will keep getting bigger and bigger. So if the modulus, and when we say the modulus, that's now plus or minus r, is going to be strictly greater than 1, then our sequence will diverge. There's the other case now when our ratio is equal to -1, and that now will oscillate. So if we have -1, if we just consider, let's take 3, okay? If we multiply now the term by -1, we're going to get now -3. If we multiply it by minus 1, we're going to end up with positive 3, then we're going to get minus 3, positive 3, and this will simply oscillate. So it's gone from 3 to minus 3 to 3 to minus 3, and that is if the ratio is going to be minus 1. Generally, we will be dealing with sequences and ultimately series that either converge now to a fixed value or now grow without limits. So let's go ahead and look at generating a basic geometric sequence. We've seen now that for the nth term, a sub n is equal to ar to the power of n minus 1. And that is something that we will use right the way through our work with geometric sequences and series. So the first term is going to be a. Then we're going to get ar. Then we'll have ar squared. Then we'll have now ar cubed. And then we will go dot, 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 right the way up to the nth term, which is ar to the n minus 1. So let's look now at a basic geometric sequence. We can say that a sub n is equal to 2 multiplied by 1.5 to the power of n minus 1. So let's look at what we've got. This now is our value of a. So a is going to be equal to 2, as we're going to take now n to be greater or equal than 1. So our first term is going to be 2, as when we sub in 1, this is going to give me 1.5 to the power of 0. The common ratio in this particular case is going to be 1.5, and then we would look now at finding n terms. Whenever you're working with a geometric sequence, I strongly suggest you collect information in a little box with the first term a, r, which is the common ratio, and n, which now is the number of terms. So let's go ahead and now look at the first few terms in this particular sequence. So I'm going to just generate the first few, and then we'll go ahead and find some more terms in the sequence. So let's take n. We will have n to be equal to 1, 2, 3, and 4. So we could have now a sub n. So if I put 1 in, we're going to get 2 times 1.5 to the power of 0. That's going to give me now 2. On the next one, I'm going to have n is equal to 2. So a sub 2 is 2 times 1.5 to the power of 1. So that's going to give me, and I'll just write it here now, as 2 times 1.5 is going to give me 3. On the next one, what we're going to have now is 2 times by 1.5 squared. So if we go ahead and do that, we can put that in a calculator. So we got 2 times by 1.5 squared, and that's now going to give us 4.5. So that will give us now 4.5. So let's go ahead and put that one on here. So we got 4.5. Then on the next one, we will have now 4 in here. So we need to do 4 minus 1, which will give us 3. And that will now give us 27 over 4, or we could say 6.75. So if we look what we've done 2 times 1.5 to the power of 0. We've done 2 times 1.5 to the power of 1. We've done 2 times now 1.5 to the power of 2, and then 2 times 1.5 to the power of 3. So all we're doing is taking a number and subtracting 1. And we can see that the nth term is going to be 2 times 1.5 to the power of n minus 1. So if we were asked now to find the 20th term, we could say that a sub 20 would be 2, instead of 20, let's write 2 multiplied by 1.5 to the power of 19. So 2 times by 1.5 to the power of 20 minus 1, which is 19. So we could generate that term now in the sequence. Let's now look at finding the nth term of a sequence given the first few terms. So say we were given now 3, 15, let's take 15, let's take 75, and let's take 375. And we were asked to find the nth term of this particular sequence. So what we want is something of the form a sub n is equal to ar to the power of n minus 1. So the nth term is a, which is the first term, multiplied by the ratio to the power of n minus 1. Now if we look at this, if I divide 15 by 3, 15 divided by 3 is equal to 5. If I do 75 divided by 15, 75 over 15 is going to be equal to 5. If I do now 375, so 375 divided by 75, that too is going to give me 5. If you're unsure, just check it on a calculator. 375 divided by 75, that will now give us 5. So from this we can see that we've got a common ratio of 5. So the common ratio is going to be 5. Our first term is going to be now 3. So we can say that A is going to be equal to 3. So we could say now the nth term is going to be A, which is 3, multiplied by 5 to the power of n minus 1. So let's go ahead and see if this works. Now this is the first term in the sequence, this is the second, this is the third, and this is the fourth. So if I wanted now the fourth one, A sub 4, that would be 3 lots of 5 to the power now of n minus 1, which is going to give me 5 to the power now of 3. So we can see A sub 4 is going to be 3 lots of 125, and we can see the fourth term is going to be 375 as I expected. So again, if I wanted the 11th term, A sub 11 would be equal to 3 multiplied by 5 to the power of 10, and we would just go ahead and evaluate that. So when we're looking to find the ratio, we simply divide backwards. We divide the second term by the first, the third, and we confirm. Don't just do the first one and rely on it. Once you've done that, collect the information in a box. So we might have now our value of A, R and N. Whenever you're working with this, just put them now in a box. A is going to be 3, R is going to be 5, and then in this particular case, we've taken N to be 11. And we will be given different values of N to now find terms in this sequence. I strongly suggest that any question you do, you just write these down. Okay, let's look at another type of question that we might be asked. We might be told the third term, so let's say the third term was equal to, let's go for 90, okay? And we might be told that the fourth term is going to be equal to 270, and we might be asked now to find the seventh term. So what we want to do is find this seventh term. So let's first define this. We would be told that this is a geometric sequence. So if we look at the third term, we can say that A sub 3 will be equal to AR to the power of 2. This is just using A sub n is equal to AR to the power of n minus 1. If we looked at the fourth term, we could say that this was going to be AR to the power of 3. So let's take that right here and rewrite this. So taking the fourth term, 270 will be equal to AR squared. AR cubed, that's a fourth. If we look at this one, 90, which is the third, will be AR squared. So let's go ahead and call this equation 1 and call this equation 2. What I'm looking to do, if I want to find the seventh term, I want the common ratio and the first term. If I divide equation 1 by equation 2, so 1 divided by 2, I'm going to now have 270 divided now by 90. So 270 divided by 90 is going to give me now 3. If I take A and divide it by A, that's just going to give me 1. So essentially the A's cancel out. R to the power 3 divided by R to the power 2, we subtract, and that's going to give me R. So straight off, I found my common ratio. So up in the top right hand corner, A, R and N. So I already know that R, the common ratio, is going to be 3. I know that I want the seventh term, so N is going to be 7. What I need to do here is find the value of A. So if I look at this equation right here, equation 2, 90 will be equal to A multiplied by R squared. Well, R squared is going to be 9, so dividing both sides by 9, we can see that A is going to be equal to 10. So we can place this in here, and we can simply now apply the formula for the nth term of the geometric sequence. We know that A sub n is equal to AR to the power of n minus 1. So A sub 7 will be equal to 10 multiplied by 3 to the power of 6. So the 7th term is going to give me 10. 3 to the power of 6 is going to give me 729. So we've got now the 7th term will be 7,290. So all I've done is simply worked out now the common ratio R. I've looked to find A, I've subbed it in and found the 7th term. Often we won't have a gap, we might be given the 5th term, and then we would simply end up now with R squared. We would take the square root and it would tell us now whether the ratio is positive or negative, or it might even ask us now to state the possible values of R. So again, that's a nice, fairly logical question. So we've looked at 3 types. We've looked at generating a basic sequence given now the nth term. We've looked at finding the nth term given a sequence. And now we've looked at a slightly more challenging question. In a later video, I'm going to do some word-based questions and look at some more problematic examples that we could use. Let's finish with one more example. We might be asked to find which term in the progression or the geometric sequence, and we'll write this down, of let's take 3, 12, and then 48, and then so on and so forth, is going to first exceed 1 million. So we want now the first term in this particular sequence that will exceed 1 million. So let's go ahead and set this up. So we want now the term. So this is going to be 3, 12, 48, and so on and so forth. And of course, this is going to be the first, this is going to be the second, this is going to be the third. So we want to say now, along this line, when we're doing this particular sequence, which term in this sequence is going to give us the first value that's going to be greater than 1 million. Now we know that the nth term, a sub n, is going to be equal to a multiplied by r to the power of n minus 1. So let's go ahead and set this up. So what we're going to have then, we're going to have 1 million, and we want now the term to exceed this value. Therefore, we will have a strict inequality. If we look, we can find the value of a by looking at the first number here. A is going to be 3. The ratio, if we consider 12 divided by 3 is 4, 48 divided by 12 is 4. That is the ratio, and n we're going to take to be n. So what we're doing, we are solving for n. So all I'm going to do is sub this now in to the right hand side here. So we got 3, and then we're going to multiply this by 4 to the power of n minus 1. So the first thing I'm going to do is divide both sides by 3. So we have 1 million divided by 3 will be now strictly less than 4 to the power of n minus 1. At this stage, we take logs of both sides. So using base 10, I take log base 10 now of 1 million, and then we're going to divide that by 3, and that now will be strictly less than log, and again, base 10 of 4 to the power of n minus 1. Using the log laws, I can bring the power of n minus 1 down. So let's go ahead and do that. So if I bring the power down, we're going to have now log of 1 million, and let's put this here, so 1 million divided by 3 is going to be strictly less than n minus 1 multiplied now by the log of 4. I can divide both sides of the inequality now by log 4. Be careful when you're dividing by the log of a number. If we have now log between 0 and 1 with 0 excluded now and 1 excluded, that is a negative number. If we're dividing an inequality by a negative number, we need to change the sign round. So for example now, if I put log 4 in here, so that's base 10, this is going to give me a positive number. Yet if I put in now log now of 0.1, we're going to end up now with minus 1. This is telling me, it's saying what power is 10 raised by to get 1 over 10, and the answer is minus 1. So make sure now, if you're dividing by the log, you check that this is not a number between 0 and 1. So now we can write log of 1 million, so let's write 1 million, and that's divided by 3 over now the log, and I'm just using base 10. You can use any base you want as long as you're consistent. Log 4 will be less than n minus 1. So adding 1 to both sides, we're going to have now log of 1 million, So 1 million, and then that will be divided by 3, and then we're taking out the log of 4, and then this will be now plus 1 is going to be less than n. So we want n to be bigger than this. So let's go ahead and do that. So what I'm going to have in the calculator, I'm going to have log, and then we've got now 1 million. So I need 6 zeros, there's 4, there's 5, there's 6. So now we're going to have this divided by 3, then I'm going to divide this by log 4, and I'm going to add 1. So let's just close the bracket off now, and then plus 1. That gives me 10.17. So we can say now that n must be greater than 10.17 dot dot dot, and so on and so forth. Therefore now n is going to be 11. So we can look now at the 11th term in this sequence to be the first one that is going to exceed 1 million by using logs. So if you're yet to meet logs, you will certainly look at them, and we can use these to solve problems involving the geometric sequence. So do be careful. If you've got now log here of 0 point something, do make sure you're turning that inequality around. Now I use log base 10. You don't have to. You can use now the natural log. So the natural log is base e. You would have got the same answer as long as you're consistent. So there we go. There's a brief intro and a few different questions. In a later video, we'll look at some more challenging questions and word-based problems.